This is question 1 of the Regression Models book, chapter on binary regression. This refers to a data set that we've been working with a lot on the last couple of chapters, and the questions now ask you to analyze that data set, which hopefully you can watch some of the previous questions and see more about the loading and processing of the data. It asks to take the number of drivers killed and threshold it at 119 and fit a logistic regression model. So something like this might occur if 119 was some regulatory limit. If there was more than 119 drivers killed in a month, then that would have set some regulatory pathway on. So again, the setting is not perfectly apt for a binary regression because there's often no reason to discretize your data like this. However, it would be nice. However, more than anything, we're just going through an example of how to fit binary regression models. Okay, so let's call drivers killed binary as a indicator, as the event that drivers killed is greater than 119. And let's just be pedantic and double check that it actually says whether or not greater than 119, not greater than or equal to. Okay. So our seatbelts are going to be this. Let's double check our new variable with a table. And we see false 98, true 94. I would like it to be not necessarily a Boolean variable, but rather a numeric variable. So I'm just going to multiply it times 1, which of course does nothing, but because of the arithmetic, it will automatically convert it. Now it's 0 and 1. Again, you could also do as dot numeric. So now we want our fit to be equal to a GLM where DKB is our outcome, PP, MMC, and law are our predictors. And we want family equals binomial. Without a sample size in question, it assumes that the outcome is binary rather than binomial. And without any further arguments, and I think binomial doesn't need to be in quotes. Without any further arguments, the binomial assumes that the link function is the logit link, which is what we want. And I need, of course, to tell R what data frame I'm looking at. Data equals seatbelts. Okay, now let's do summary of fit to look at our coefficient. And I'm just going to grab the coefficient table like I often do because it's easier to display for recording. And this is a lot of numbers. I often like to round my estimates to 3 or 4 decimal places. Let's just do 3. Okay, that makes it easier for me to read at least. So now, what this is suggesting is that the logit scale odds of having greater than 119 drivers killed that month is negative 0.616 lower after the law had taken effect than before. Or conversely, MMC was our kilometers converted to 1,000 kilometers and then centered again, so our intercept has a little bit more meaning. This minus 0.003 means that we estimate a logit scale change in the odds of greater than 119 drivers killed that month as being 0.003 lower for every 1,000 kilometer increase in driving distance. So we would like to take some of these numbers and exponentiate them, because that's often maybe a better interpretation than the logit scale. Okay, so if I exponentiate the law coefficient, okay, I get 0.54. Okay, and so that means that the odds, the odds ratio, comparing when the law was enacted to before the law, right? 1 on the numerator, 0 on the denominator, was 0.54, or we can 1 minus this and say that there was a 46% decrease in the odds of drivers, of greater than 119 drivers being killed in a month after the law was enacted compared to before the law was enacted, holding the other variables constant. Okay, let's look at exponentiating this one. We know that this is going to be about a 0.3% decline. So let's just 1 minus it just to remind ourselves. So this variable, which was miles, represents a 0.3% decrease in the odds of greater than 119 drivers getting killed in a month for every additional 1,000 driver miles that month. Okay? So those are the interpretation of some of our coefficients, and that's how we would fit it.